All right, here we are. We are on. Super thrilled to be here. Myself, Vaibhav, and with me is my colleague, Andres. We are from the Google's cloud networking team, Cloud Load Balancing. And the reason why we're here, as you might not know, Google's Cloud Load Balancing is based on Envoy Proxy, all of our application load balancers. And we've been doing a lot of work on AI serving, LM serving as part of Google Cloud Load Balancing, and also upstreaming all of that work into Envoy Proxy. So trying to represent that, but also represent a lot of the work across a number of different projects and different companies that are working in this space also on Envoy. Okay. So jumping right in, talking about what are customers looking for in terms of consuming LLMs. Some of the same things that you'd have from any enterprise service, right? Having simple access, especially with different LLM providers, having different sort of interfaces for consuming their LLMs. Developers primarily, are looking for a simple way to access all of these services and LLMs. Doing it securely, so this is especially trying to getting applications into production and moving them from development. Security starts to become top of mind, and even from your development environments, how do you avoid key sprawl? How do you have like the kind of right credential management and guardrails? Reliability, again, especially as these workloads start to scale up. We know that GPU, TPU capacity is still very constrained, and having reliable access to these LM services is still very much takes some engineering effort and consideration. Finally, you want your applications and even your LM serving to be fast, right? User experience matters, and to have that kind of low latency response, and then finally cost efficiency, right? These things are expensive to run, and being able to do it cost efficiently certainly is again another top of mind. So with that, we'll just look at given these kind of high level requirements, what are the different adoption patterns? What are the different deployment models that we see often customers deploying? So customers we see often are consuming LM services from a variety of different model providers. Could be from your Hugging Face, could be from Bedrock, could be from OpenAI, Vertex, so on and so forth. And in conjunction, they could also be deploying models on their own clusters. And so with these sort of situations, they often end up requiring some sort of an API gateway to front end all of these different APIs from all of these different LM providers to have, again, that simplicity primarily, but also some of the security aspects. Then you've got customers who are deploying models on their Kubernetes clusters. We see this pattern, especially as customers start to scale up their workloads. They're looking for better cost performance, price performance, and also like better control of the infrastructure and being able to fine tune it. And so that's where a lot of Kubernetes deployments, and similarly, for customers who have standardized on service mesh patterns, they're also deploying these LMs and publishing them as services in their own service meshes. And then the other pattern we see emerging quite a bit is that all of these LMs now are not only, you don't just have like clients or service applications connecting to LLMs, but now LLMs calling out to tools or even like things like MCP servers. Now that Anthropic has come up with a standardized way to allow third parties or applications to expose their services to LLMs. We see a lot of these sort of egress deployment patterns from LLMs to third-party tools and services. And that's another area where, kind of showing where Envoy fits into each of these data plane paths. And it's as you can see here, it's egress, ingress, as well as mesh patterns that it's applicable in. So diving a little bit deeper into the particular considerations traditionally in each one of these deployment paths. So in terms of like consuming LMs from a variety of different providers, we spoke about that you go to OpenAI, they have a certain API spec, go to Anthropic, they've got a different one, Gemini, Bedrock, like everybody has got their own API spec on how to consume models, and that's like an additional overhead for your developers, right? So with API gateways, having a single consistent API surface, being able to very easily discover all the different models and the providers that are available for developers to use, That's something that AI gateways or API gateways often provide you with. The second one is also on the security side. So instead of developers, everybody just having to embed, in a bespoke model, some sort of AI security safety into their own code. And again, why this matters is, as you might have seen, that LMs by themselves may or may not have the kind of necessary guardrails and checks against things like jailbreaks or prompt injection attacks. So these things that, or even like things like safety controls, right? These are things that the LLM themselves might not provide. So that comes like either the developer has to do it, or the platform operator or your central security team would have to have something in the path to apply these guardrails. So just by natively developers accessing these LLMs might give you fragmented coverage. Having some sort of an API gateway where you could attach some sort of AI guardrail, an AI security check, provides you a better level of security. And then also you don't want like just developers using API keys and tokens all over the place, right? Having some sort of centralized control, some kind of lifecycle management for them, and also being able to like consistently allow developers a single way to manage security, while in the back end you can have some sort of a LLM provider specific authentication authorization mechanism. So that really simplifies developers' lives. And then finally is the aspect of centralized logging and cost management. When it comes to self-hosted models, the particular challenges that we see is especially on the number one reason that customers go to this model is to get better price performance. But to get better price performance, if you just look at traditional load balancing, what we've seen, especially with customers serving LLMs at scale, is that your traditional round-robin load balancing schemes are not a good fit for serving LLMs. So what happens with LLMs is that the requests are highly variable in duration, so it could vary anywhere from seconds to minutes, as compared to traditional web serving, where the request is only in the order of milliseconds. So when you've got such a variable traffic distribution pattern or workload pattern, and if you use things like round robin, what ends up happening is that the load gets unevenly spread out across your backends. And as a result, what that means is that you get lower or suboptimal serving performance. And so that's where a lot of work has been, we'll talk about in detail, is how you can evolve load balancing for better serving based on the workload characteristics of these LLM workloads. Okay, so in a nutshell, across all of these challenges, what the effort on Envoy Proxy is doing is to address all of these, both in terms of the API gateways, in terms of service meshes, in terms of Kubernetes ingress, and bring in a whole set of enhancements to better serve LLMs, right? Starting from, a lot of this is enabled through extensions and natively get embedded into Envoy Proxy natively. But at least from including across extensions, being able to provide a unified API surface for different LLM providers, being able to route based on the model name, and we'll learn a little bit about that, what that means. Being able to add security guardrails as part of the data path, and being able to add things like, whether it's Google's own Model Armor, or even third-party tools like from Palo Alto Networks and from NVIDIA NeMo guardrails, all of these in part of your data plane. We always had client authentication authorization, but being able to do it across different LLM providers. Again, and then in terms of the speed and performance, so Envoy by itself natively has a very high performance data plane, but now we are also evolving the load balancing capabilities of Envoy to be more catered towards LLM workload patterns. And then finally, in terms of reliability, being able to serve across multiple backends, being able to have like routing policies, again, based on the model name, that helps you drive better reliability. And then also in terms of cost efficiency, being able to do things like token-based rate limiting. Okay. So we'll deep dive into there's essentially two key extensions that we'll go deep dive into. But just kind of showing you how extensible Envoy is for these sort of use cases. The first one Andres will talk about in more detail, is about how we have evolved it for doing model name-based routing. The second one is around how we are going to be doing load balancing that is more tuned for LM workloads to give you better performance. And then finally, taking the same pattern and extending to other use cases like AI safety or even things like semantic caching going forward. So with that, we'll deep dive into each one of these and hear Andres to talk about that.
All right. Thanks, Vaibhav.
Yeah.
I'm just going to hang out over here. All right. Hello, everyone. So I'm going to focus on how we're evolving Envoy for these capabilities. The slides that we've prepared are mostly focused on the self-hosted inference use case, but these patterns will generalize to the other use cases that Vaibhav just mentioned, like API gateways and service mesh. So the first use case we want to talk about is model-aware routing. So this involves being able to actually create routes that are pointing to specific models as opposed to just your pool of compute. The key challenge here is that GenAI protocols are not really optimized for networking. And currently, they require us to be parsing the request payload in order to actually determine, for example, what the model name is, and extract, really the key attributes that we need for routing, right? So the end goal is that we want to have native Envoy support for things like body parsing and body transformations. There are Envoy issues filed around this. And one thing to call out is that some of these capabilities will require significant buffering, while others can leverage streaming support depending on the protocol. Thankfully, these protocols are currently JSON-based, so there's a path towards streaming parsing. But if you're making a routing decision based on this data, then you need to buffer, right? So the way that we're approaching this right now is that we're using Envoy, until we have native Envoy capabilities, we're using extensibility. And we've created this thing called the body-based router to handle the parsing, the attribute extraction, and the routing. So how does this work? So we're using extensions, and for the majority of this talk, I'll be talking about actually XProc-based extensions. And what the extension really does here is that it registers for request header and body events. It does the necessary attribute parsing, and it ends up appending a header. Let's call it X gateway model name that is then matched in the route configuration with a header match to select the corresponding cluster, right? So we've effectively externalized the body parsing. That gives us a nice property, which is now the buffering is also externalized, which some use cases will require depending on your body sizes and your prompt sizes. And that's effectively how we're handling this challenge with model-aware routing. So I've mentioned XProc a couple times. So just to give a bit of background on what that is, it's a filter that essentially calls out via gRPC to external services at various HTTP lifecycle stages. So you can specify whether you want to receive request headers, body, trailers, and same for that response path. It provides both the HTTP attributes, right, either the headers or the payload, along with any configured dynamic metadata namespaces. It can be used to influence Envoy cluster picking, which is what we saw with the body router. It can also be used to influence endpoint picking decisions, and we're going to get into that in a few slides. And it also has a nice property that when you have these extremely large payloads, you can externalize the buffering to this callout service. So there are some notable recent Envoy enhancements in this space. I listed a few PRs. There's work being done for XProc scalability. There's also work being done to enhance the endpoint picking capabilities that Envoy has using XProc. OK, so the second major part of this evolution then is inference optimized load balancing. And there are really two key components here, right? We have the first major component is we want an inference optimized algorithm, a load balancing algorithm, right? And I'm not going to do a deep dive on model server token generation as part of this talk because that's its own separate talk. But really the key things to note are that a lot of these algorithms right now are focused on managing this key value cache that's used to store intermediate outputs from the LLMs, and really prevent saturation of that cache. So that's one of the key things that the algorithms are doing now, as well as managing these pending request queues that are also building up in model servers. Okay? So in order to do that, these inference optimized algorithms require load signals directly from the model servers. And that's sort of the second major component, is that we've built infrastructure, this Orca mechanism that's now in Envoy, to be able to receive load signals from the model server directly. And then what we end up with is this architecture where you have, an algorithm implemented via extensions, receiving load signals from the model servers. And those load signals can also be joined with system metrics that are being, for example, are being consumed via a separate pipeline that the platform orchestrator provides potentially. And all of those signals are now also being provided to the load balancing control plane through LRS, through the load reporting APIs. And that allows the control plane to also make higher level traffic distribution decisions, such as varying the locality weights. So you can actually pick, let's say what zone or region you want to load balance to. So focusing on that first component, right, the inference algorithms, we have new algorithms that are actually using these application load signals to load balance. There's a new client-side weighted round-robin algorithm that computes endpoint weights based on the reported utilization metrics, as well as the request and error rates. There are also existing algorithms such as least request that can be enhanced to support these new metrics. However, for optimal request placement, we've really found that we need high iteration velocity to keep up with the rapidly evolving GenAI models and their implementations. And inference really requires additional algorithmic complexity due to just the characteristics of the model servers and token generation. So what we've ended up with is, we're leveraging Envoy's extensibility capabilities again. The open source machine learning and AI community has really coalesced around a few languages such as Python, right? So we really want extensibility options that are language agnostic. And leveraging extensibility also gives platform builders the ability to bring your own extension capabilities, which is something that end users want. They want portability. They want to be able to modify the algorithms as needed. Going back to that second component of optimized load balancing is this new metrics collection, right? So the key pain points there are that inference requests are on average 1,000 times more expensive than traditional web workloads, which means that if you misplace one of these requests, it's just much more expensive, and you can really feel it in your tail latency. Also load signals cannot be observed by Envoy directly, right? These model server metrics for key constrained resources are required instead, and this is where the KV cache utilization and these queue depths come into play. And then there are also very high GPU and accelerator costs, right? So the traditional approach maybe of over-provisioning your backends is really undesirable and really not viable in many cases, right? So the solutions that we've come up with is to introduce this new load collection mechanism, Orca. Misha Efimov in the audience will give us a lightning talk later today on a deep dive, so I'm not going to go deep into that. But really, the basics are that there is an inline collection mechanism right now through HTTP response headers. And next, we plan to introduce out-of-band collection mechanisms where you can do probing before you actually pick the endpoint, and also asynchronous probing on a regular interval. And this is really required for long-lived requests, for streaming requests, and that's really a common case with LLM serving, is that we really want to decouple the load signal collection from the QPS, essentially. And the last thing here is that it's integrated with the control plane via the load reporting APIs, via the XCS APIs. Okay. So now that we've gone over this architecture and the pattern, right, I wanted to provide a concrete example of how we're leveraging this for a solution to users. There's an open source project right now that's being incubated in the Kubernetes serving working group to enhance the Kubernetes gateway APIs, which are the abstractions in Kubernetes for load balancers. To provide an extension-based approach for inference-optimized routing and load balancing, right? So these new CRDs, these new custom resources, specify both an API contract Essentially, how do you do model-aware routing? How do you specify policies per model or per inference pool? But also, they're also specifying an extension protocol contract that's based on XProc. And the APIs themselves, right, we have these objective-based policies currently around this notion of criticality, which is, do you have a critical, standard, or sheddable workload? There's also the ability to operationalize LoRa, which is a fine-tuning mechanism that allows the model server to dynamically load weights. And then there's also model-based traffic splitting as part of these APIs. And then we're also planning to introduce new capabilities soon, such as prefix cache-aware routing, which is another inference optimization where you're really trying to reuse the KV cache that I've discussed across multiple requests. And really the key goals with these APIs and these extensions are portability and also compatibility with the existing Kubernetes gateway APIs, with the existing Envoy APIs, right? So that you're not really losing all of your existing proxy or load balancing capabilities when you want to use the inference optimized extensions. And what we've ended up with right now is we have both a body-based router that we already discussed, and we also have this new extension also called an endpoint picker. So this is the inference extension architecture, right? The more concrete architecture with these new components. We can see that we have the body-based router that provides the model-aware routing via this header that then gets matched in the Envoy route configuration. We also have this endpoint picker extension component that's implementing the inference optimized algorithm. Right, and then we have the application or the model server load signals that are being propagated to both the extension and also the load balancing control plane. And this is essentially how we've put together a full solution, including existing capabilities that the end users were depending on, such as any sort of DOS protection and Auth-Z support that's provided either as another extension or natively in Envoy. And just diving a bit deeper into the extension, into this endpoint picker extension, what it's really doing is it's determining the endpoints that Envoy should select. And what it's doing is it's scraping relevant model server Prometheus metrics, such as the KV cache utilization and dependent queue sizes. You will also support Orca in the near future. It ranks available endpoint capacity based on the scraped metrics. It tracks dynamically loaded LoRa weights per endpoint. So it does LoRa-aware routing and soft affinitizes the requests accordingly. It prioritizes critical over sheddable traffic. This is how it applies these objective-based policies. And then soon you will also be able to do this prefix cache-aware routing that I was talking about. And the way that this is actually implemented is that we have XProc metadata. And then when the endpoint picker runs its algorithm and picks the endpoint, it returns in the XProc response metadata keys that essentially tell Envoy which primary endpoint has been selected, and also which fallback endpoints are selected, so that if it needs to retry, it can actually retry to a different endpoint. There's also this capability that we've introduced to allow the proxy to provide a subset of endpoints that the endpoint picker should select from. That allows it to do filtering if you need to do some pre-processing to effectively filter out the undesirable endpoints from the endpoint picker extension. And what's the actual value in doing this, right? So I'm just providing just a basic set of benchmarks that have been run. And these charts were generated using a benchmarking environment with 10 VLLM model servers using H100 GPUs, the Llama 2 7 billion parameter model, and the shared GPT dataset, right? And we're comparing the blue line, which is the inference extension Envoy versus just Kubernetes cluster IP load balancing. And we can see that while the throughput largely remains unchanged, and the thing that we need to call out is that there's no major penalty for doing this inference optimized load balancing. But we do see a very significant reduction in per output token latencies with extension algorithm, and we also see significant reductions in tail latency, especially as you ramp up QPS. And yeah, and just closing out, right? So we've talked about two of the use cases for extensions, which are routing based on the request body payload, the custom load balancing algorithms, but this also can be applied to both applying security and AI safety policies, right? It can be applied to other capabilities that are desired for LLM serving, such as semantic caching. Excuse me. The key thing is that composability is required, right? We need to build this in a way that you can actually chain the extensions. And the last thing I want to call out is that we focused on XProc right now, but once WASM becomes stable, right, we do think that this is probably going to become the optimal choice for some of these use cases, and especially because it will provide a much simpler operational experience for the extension providers, right? They're not going to need to manage an external service, so we think that there are some big wins to using WASM. And lastly, we just wanted to call out these ecosystem implementations. So these are, community projects that are either using extensions for their own use cases, or they're actually implementing these Kubernetes gateway inference APIs. Envoy AI Gateway, K Gateway, Istio, GKE Gateway, and VLM production stack. And that's all we got. So. Thank you.